In this video, we're going to take a look at trace concentrations, and we're mainly going to focus on the units of parts per million and parts per billion, which you're likely going to encounter in a general chemistry course, or you're definitely going to encounter in an analytical chemistry course at some point in your career, or if you're not even in school, you're probably going to see this at some point in your life dealing with manufacturing standards or a whole slew of things that I probably can't even imagine, but you're going to see it. So let's take a look. So here's how most textbooks define parts per million or parts per billion. So they're going to say grams of analyte, the substance that we're studying, over grams of the whole solution, times 10 to the 6 for parts per million. And then for parts per billion, it's going to be grams of analyte over grams of solution times 10 to the 9th. And this is a good way to sort of, as a beginner, to look at it. But if you're doing the stoichiometry and all that, I think there's a faster and more efficient way to memorize what parts per million and parts per billion are. So for parts per million, I like to think of it as micrograms of analyte over grams of solution. So, for micrograms, that's, a millionth of a gram. And this sort of roughly approximates, not roughly, at times it depends on the density of your solution, 2 micrograms of analyte over milliliters of solution. I think this is the fastest way to memorize it if you're studying for an exam. So, and why is it that micrograms of analyte over grams of solution roughly equal micrograms of analyte over milliliters of solution? Well, basically what's happening here is the mass of the solution, or the solution has a density that's equal to 1 gram per milliliter. So let me prove this with the stoichiometry real quick. So let's say I have 1 gram or 1 microgram of something, and that's in 1 gram of solution. Now, if I wanted to convert that using the solution's density, if we assume the solution has a density of 1 gram per milliliter, then it's just 1 gram up here and 1 milliliter down here. Grams cancel, and we get 1 microgram per milliliter. And typically you can make this assumption unless it's stated otherwise. All right, let's take a look at a problem real quick. So they're asking us to express a really small molarity of lead ions in parts per million. And I think this problem really exposes the need for the parts per million and parts per billion unit, because firstly, I mean, this is a ridiculously small molarity, and I don't think it would be that. I mean, you could maybe express it in micro molar or something like that, but typically when you get some sort of report from the Environmental Protection Agency or something like that, they're going to tell you we want lead to be below, whatever parts per million or parts per billion. And so you want to be able to convert your molarity into these units. So let's do it real quick. So we have 0.0000001 moles of lead ions over 1 liter of solution. So first off, I'm going to convert the liters into milliliters to get it into sort of that micrograms per milliliter that we defined parts per million to be. So for every 1 liter, I've got 1,000 milliliters. And then for every 1 mole of lead, I have, I believe it's 207.2 grams of lead. And so are we done? At least for the stoichiometry part. And the answer is no. So we have to convert grams to micrograms. So for every 1 gram, I have 10 to the 6th micrograms. And let's see what that gives us. That gives me 0.2072 micrograms per milliliter, which is equivalent to 2072 parts per million lead ions. All right, and that's basically it. I'd keep practicing these problems. Most of them are going to go something like this. So good luck and have a good one, guys.